Hi, hello, good evening, one and all. Welcome to the session. Uh, can anybody confirm about audio and video? Is audio and video clear? Just give me 1 minute so that I can set the things. Yes. Please confirm, guys. Hi, hello, good evening, one and all. Welcome again. Welcome to the session. If anybody is there, please do let me know. All right. So I think you might have come across this series, Isro series. I think already so many faculty have taken the questions from each and every subject, and I am going to take up some questions on electrical machines. I think already Ashu sir has taken about the previous year questions of ISRO on electrical machines. I think he might have covered the questions on power systems as well as power electronics also. So please go through them so that you will get an idea uh, in what way or what are the levels of the, or what is the level of the ISRO question paper. I don't think it is going to be a tough paper, but it is going to be a concept based question or fundamental questions you can expect. Okay, so those are the questions you can expect from ISRO. So the same kind of questions I brought here. Please look at, we'll discuss those kind of questions here. I'll try to, maybe this is a 30 minutes or 40-minute session, so I'll try to discuss some questions on transformer as well as induction motor. Okay, if time permits, I'll take up some more questions on DC machines also, because I tried to take some questions from each and every topic. Those are very important, right? So if time is not permitted, then I'll try to plan another session so that we can discuss some more questions from DC machines as well as synchronous machines. Okay. Hi everyone, good evening Sweta, how are you? So please let me know your presence and show some reactions so that we can move on to the session. Before moving on to the session, there's a small introduction about myself. My name is Naveen Gollapalli. I have 11 plus years of experience in teaching. Most of the times I'll be teaching electric circuits, machines, measurements and power systems. I cracked GATE and State Public Service Commission examinations also. I have taught more than 20,000 students since 2012. So there's a small introduction about myself. Okay. If you have any doubts at any point, please try to post your doubt in the comment box so that I can take up your doubts and I'll try to reply as soon as possible. Okay, and moreover, if you have any doubts in any other subjects also of electrical engineering especially, you can write a mail on this mail ID naveen.gollapalli@byju's.com. You can take up a screenshot of that question and try to post that question on this mail ID. I'll try to give a reply as soon as possible within one day. Okay, right. Uh, right, so we will start the session, and before going to start the session, there is a small introduction from the BYJU'S exam platform that is called Trickopedia. This Trickopedia is like same YouTube chats only. We will be having a we will be discussing the tricks to solve the questions. Like when you have a question with 4 options, we will be giving you the hints and tricks how to eliminate at least 2 options, like how to eliminate the options by looking at the questions in that manner. We will be giving you the tricks and tips in this series. Okay, so this series is going to start from 15 June. So if you have not yet subscribed to the BYJU'S exam prep channel, please subscribe so that it will help you in understanding the questions and tricks. So okay, we'll move on to the session. So let's move on and try to share this session with your friends and colleagues, those who are preparing for ISRO 2023. Okay, chalo guys, we'll move on, and please do let me know your presence. Apart from Sweta and others, please do let me know if anybody is there. Please do let me know. Okay, so look at this question. Look at this question. I have a question that is on transformer. So I have around 8 to 9 questions on transformer. First 8 to 9 questions will be on transformer, and the next 8 to 9 questions will be on induction machines. If time permits, we will take up some more questions on DC machines also, as well as and synchronous machines also, if time permits. Otherwise, I'll plan for another session. Okay. So the question is about the function of conservator in transformer is. The function of conservator in transformer is. So this kind of don't think that this kind of question appears in the examination or not. Don't ask that kind of questions, because some basic questions, some silly questions also, simple questions also you can expect, because when they are going to set up 70 to 80 questions, if they wanted to cover all the questions, they cannot create all tough questions, right? There should be some easy questions also. So that's the reason why I brought, and these are the PSU's model questions only. Okay. So good evening, Ashok. Hi, how are you? So post your answer as well as post your answer in the comment box, and try to make the session very interactive, so that we can make the session very beautiful. Yeah, after a long time. I am fine. Okay, tell me the answer for this one, guys. Tell me the answer for this one. The function of conservator in the transformer is to take up the contraction and expansion of the oil, or the option B is saying to cool the windings, option C is saying to prevent the moisture in the transformer, option D is saying none of the above. Obviously, none of the above is not going to be the answer. And when it comes to the C, to prevent the moisture in transformer, so to prevent the moisture in transformer, this will be done by Buchholz relay. This will be done by Buchholz relay, not conservator. So after the conservator, there will be a small pipe, and in that, at that pipe, end of the pipe, you will be having the I am so sorry, this is not Buchholz relay. I am so sorry. Breather. Just a minute. It's a breather, not fault. Internal faults will be identified, and it will be tripped with the help of Buchholz relay. To prevent the moisture, it will be actually done by the breather. I'm sorry. When it comes to to cool the windings, this will be done by the oil, transformer oil. So obviously B is not going to be the answer, C is not going to be the answer, D is not going to be the answer. You can take up the answer as this one, contraction and expansion. So when the transformer is operating, because of heat dissipation from the windings, because of heat dissipation from the core, okay, when they are carrying full load currents, or when they are carrying some certain amount of currents, definitely heat dissipation will be there. And because of that heat dissipation, that heat will be absorbed by the oil, and due to that temperature rise, the oil tries to expand and contrast. So if you do not have a conservator, so there might be chance of damage of tank also. So in order to save, or in order to avoid the damage for the tank, we will be providing conservator at the top of the tank through a pipe, so that the oil can expand and contract, so that the heat can be dissipated easily into the atmosphere. All right. Okay. Let's we will move on to the session. We will move on to the next question. The next question is again from the transformer. The question is about if a transformer fed from a fundamental frequency voltage source, the source of harmonics is. Option A is saying about overload, option B is saying about poor insulation, and option C is saying about iron losses, option D is saying about saturation of the core. If option D is not visible, let me hide myself. Option D is saturation of the core. I am writing aside. Option D is saturation of the core. So please post your answers. Please post your answers in the comment box. Guys, try to share the session with your friends, those who are preparing for ISRO. Sweta is saying D. Others? Ashok is also saying D. Very good. D is the answer, no doubt, because the non-linear part in the transformer is core, because core is meant for to establish the flux lines, because windings will carry the current. If it is a primary, now we will give the supply and it will carry current, so it will produce the flux lines, and that flux has to establish through the low reluctance path, that is called core. And if the flux is establishing through the core, when you have a winding on the secondary, this flux lines will link with the secondary winding and creates an EMF here. So that is how the power can be transferred from electrical energy, that is how the power can be transferred from one side to another side through electromagnetic energy conversion. Okay, so here the core is going to carry the flux lines, right? Now the flux establishment is directly proportional to, actually should be directly proportional to current, but it's highly impossible to have this kind of linear relation. It's this is a linear relation. Okay, so it's not possible. If 1 ampere current is flowing, 1 Weber of flux you cannot expect. 2 amperes amount of current is flowing, 2 Webers of flux is not possible. So definitely not possible. That linear relation is not possible. You will be having non-linear relation, and that's the reason why the BH curve, if you look at the BH curve, the pH curve will be like this. For certain distance or certain values of current, it will be linear, and then it will be saturated, and then it will be deviated, and it will be like this. So this is how the BH curve stands. So the BH curve is a non-linear because of two reasons. One is the saturation, another one is going to be magnetic inertia or retentivity property of the magnetic material, I can say, or we can also call it as hysteresis non-linearity. So this is the hysteresis non-linearity, and this is the saturation non-linearity. So those are the two reasons because of core. Saturation of core is not only the reason. Hysteresis non-linearity is also reason for the production of harmonics. So harmonics is not just because of saturation of the core, and hysteresis non-linearity also. Okay, so these are the two reasons. Okay, so let's move on to the next question. The next question is, he has given it as a 230 volts by 2300 volts transformer takes no load current of 5 amperes at 0.25 power factor lagging. The core loss is, he has given it as A 300.2, B 192.5, and C is 212.6, and D is 287.5. So if the options are not visible, let me write aside. It will be C is 212.6 and D is 287.5. So try to solve and tell me the answer. Sweta, Ashok and others, please do respond. He is asking core losses. You can find out the core losses in open circuit. So in the open circuit, whatever the wattmeter reading is there, that wattmeter reading is nothing but core loss. Majorly that is a core loss, and minor loss will be due to copper losses. So I can write the wattmeter reading as the voltage applied on the no load and the current drawn on the no load and the power factor on no load. So if you take up, the voltage is 230 volts, current is I0, no load current is 5 amperes, and the power factor is 0.25. 0.25 it will be 1 by 4. So you can take up 1 by 4, 5 by 4 into 230. You will get it as how much you are going to get? 4 6 24. Probably how much you are going to get? Anybody? Again you are getting D, 230 into 5 into 0.25, 287.5. 287.5 could be the answer. Alright, very good Ashok and Sweta. Let's move on to the next question. Please try to respond. Please try to respond and try to solve the questions. Very good. Okay. Look at this one. The purpose of performing Sumpner's test mainly to find out. We will be having few tests are there on the transformer. You can work out. Open circuit test is to find losses in the core. Short circuit test is to find copper losses in the windings. Okay. Now Sumpner test is because of what? There are so many tests you can conduct, like polarities test, this, that, that, insulation test. So many tests are there. Now what is the purpose of Sumpner test when it comes to the transformer? So is it to find out the regulation of the transformer, or is it to find the efficiency of the transformer? Is it to find the temperature of the temperature rise on the full load, or last one is none of the above? Last one is none of the above. Very good, Ashok. It's Sumpner's test. Sumpner's test is a heat run test. Yeah, you can also call it as temperature rise test. Yeah. So let me tell you here. I said as at the beginning of the question itself, open circuit test will give you the core losses or iron losses, minorly copper losses. Short circuit test will give you copper losses and minorly core losses. Okay. So when you perform open circuit test, you are not getting major copper losses. When you perform short circuit test, you are not getting major iron losses or rated iron losses. Okay. So here let me write open circuit test. You can find out iron losses, but not rated copper losses, but not full load copper losses. This can be done rated iron losses. Iron loss are rated, and short circuit test will give you full load copper losses, but not rated iron losses. Okay. So in one test we are able to find one rated loss, another rated losses we are not able to find. So the combination of open circuit test and short circuit test will be the Sumpner test. Okay, we will be taking two transformers. And we will drive the transformers on the full load. So we will get rated iron losses, we will get rated copper losses. What will happen because of this Sumpner test is a question. Okay. When you conduct open circuit test, copper losses are not rated, so you are not going to get exact heat dissipation. When you conduct short circuit test, iron loss are not rated, not full load, so you are not going to get exact heat dissipation, or what is the heat dissipation at rated operation condition, we are not able to find. So through the Sumpner's test, you will get rated iron losses and rated copper losses. Rated iron losses and rated copper losses. So as the losses are happening at rated condition or full load condition, the heat dissipation due to iron losses, the heat dissipation due to copper losses will be taken place full load, according to the full load, and therefore the temperature rise is more compared to open circuit test and short circuit test. Okay. So here the main intention behind the Sumpner's test is to find the temperature rise on the full load. Now my question is, what is the use of finding temperature? What is the use of what is the use of finding the temperature rise? Let it be 27 degree Kelvin, or let it be 100 Kelvin, let it be 300 Kelvin. What is the use of finding temperature rise with this Sumpner's test? When you are able to find out when you are able to find out iron losses, when you are able to find out copper losses with open circuit test and short circuit test, what is the use? Can anybody tell me what is the use? Okay, think and tell me. Meanwhile, we will move on to the another question, that is, a two-winding transformer is converted into an auto transformer. Okay, if we apply additive polarity and subtractive polarity for the connections, Then the secondary voltage is 2640 and 2160. Okay, so we have a 2-winding transformer. Probably let me write the options here if it is not visible. 66 is to 54, 54 is to 66, 10 is to 1 and 1 is to 10. So I have a 2-winding transformer and the 2-winding transformer is converted as auto transformer. So let me take up it as auto transformer. So this is my first winding and this is my next winding. So what he is saying is, if we apply additive polarity, so let me take up the dot here, let me take up the dot here, so you can have a additive connection. So this is an additive connection. So if we apply additive polarity, the voltage is going to be 2640. So I can say this is one winding and the winding voltage is V1, and this is second winding, the winding voltage is V2. So if you add up them, V1 plus V2 is equal to 2640. Similarly, if you subtract, if you connect them with the subtractive polarity, the voltage he is saying it as 2160 volts. So let me take up here it as, again this is going to be V1 and this is going to be V2. Okay, so V1 minus V2 is going to be 2160 volts. Okay, so this is the secondary voltage in the auto transformer. After connecting into auto transformer, that is the available voltage on the secondary side. So additive V1, what is V2, what is V1 and V2? V1 and V2 are the voltages of the 2-winding transformer. V1 and V2 are the voltages of the 2-winding transformer. Okay, now if I connect it in additive manner, this is the voltage available in the secondary side. If I connect in subtractive manner, subtractive polarity, this is the voltage available in this on the secondary side. Okay, so I can take up the equation like this. Now what is asking, what is the ratio of primary to secondary voltage? The ratio of primary to secondary voltage. So V1 to V2 is asking. V1 to V2 is asking. Can anybody tell me? Sweta is saying C. Anyone else? Okay. So we can solve this equation. I want V1 and V2 values. So let us solve these equations. 2640 and V1 minus V2 is equals to 2160. So you can cancel out this V2 values and 2V1 is equals to 4800. So from this one I will get V1 is equal to 2400. V1 is 2400. If V1 is 2400, what is V2? If you substitute any one equation, you will get it. So, and V2 will be, if V1 is 2400, V2 will be 240. Now, if you can take up the ratio, it will be 10 by 1. 10 by 1. So, C could be the answer. Ashok is also saying C. Okay. I asked one question. What is the use of finding out temperature rise from the Sumpner test? Why? Are you going to use the temperature information anywhere while calculating the regulation, while calculating the efficiency? While calculating the regulation, we will be taking the use of resistance, we will be taking the use of reactance, and that can be calculated from short circuit test. When you calculate the open circuit test, we will be taking the help of iron losses, we will be taking the help of copper losses. Copper losses can be calculated from short circuit test, and iron losses can be calculated from open circuit test. Now if you perform Sumpner's test, you will get temperature rise. Now where do you use this temperature rise in analyzing the transformer? That is my question. If you perform open circuit test and short circuit test, we can take the data and we can use it to calculate regulation and efficiency of the transformer. My question is, why are you performing Sumpner's test? Why are you performing Sumpner's test? Okay, the answer is to find the temperature rise. Now where do you use this temperature rise is the question. Did you get me? So if you get me, please try to answer that question. So let's have one more question. The question is about a 2 kVA transformer has an iron loss of 150 watts and full load copper loss of 250 watts. Okay, the maximum efficiency of the transformer would occur when the total loss is asking maximum efficiency can takes place or would occur when the total loss is. Okay, what will be the total loss at maximum efficiency condition? That is what he is asking. If options are not visible, let me show you the options also. The options are 500 watts, 400 watts, 300 watts and 275 watts. Ashok is saying 300 watts. Okay. If options are not visible, I am writing here 500 watts, 400 watts, 300 watts and 275 watts. Okay. See, here he has mentioned the iron losses are 150 watts. So whether the load is going to be no load or half load or full load, okay, half load or full load, doesn't matter. Irrespective of the loading, the iron losses are going to be constant all the time. From no load to any load, the iron loss is going to be same. You don't expect much change. Okay, if the load is going to change, iron losses won't change. Even it is greater than full load also, the iron losses are going to be all the time, it is going to be constant. Okay, all the time it is going to be constant. Now with respect to the load, the copper losses can change. With respect to the load, the copper loss can change. All right. Now if the load is going to be changed, the efficiency is also going to be changed. Now if the load is 0, I can say that open circuit, so I can say current is 0. If current is 0, output is 0 and efficiency is also 0. If load increases, current increases and output increases, your efficiency also increases. Maybe at certain point of load, I am not saying it is half load, maybe greater than half load or 75% of load, the efficiency has become maximum and then it is decreasing. If you go beyond 60% of the load, let us assume if you go beyond 60% of the load, the efficiency is again falling, which means from no load to 60% of load, the iron losses are dominating the copper losses. Okay, now at 60% of the load, the copper losses are going to be equal to iron losses, and this is where the maximum efficiency is taking place. Don't expect the maximum efficiency at full load condition. It's not possible. Okay, if the transformer is unless it is designed to give the maximum efficiency at full load, it will, otherwise it will not give you. Okay, the transformer can give the maximum efficiency at any point. Okay, so greater than the 60%, the copper losses are going to dominate the iron losses. Okay, so I'm assuming 60% of the load is going to give you the maximum efficiency. Now at maximum efficiency, you look at the losses. What is happening? The copper losses are becoming equal to iron losses. If the load is less than 60%, copper losses are less than iron losses. If the load is greater than 60%, the copper losses are greater than iron losses. And this is the point where the copper losses are becoming equal to iron losses at maximum efficiency. So that is what he is asking. At maximum efficiency, the maximum efficiency of the transformer would occur when the total losses is. So at maximum efficiency, the total losses will be simply equal to iron losses plus copper losses. I can replace the copper loss with iron loss, but I cannot replace the copper loss with iron loss. I cannot replace the iron loss with copper loss. I can replace the copper losses with iron loss, but you cannot, don't try to replace the iron loss with copper loss, especially full load copper losses. That will give you wrong answer. So it is going to be 150 plus 150, you are going to get 300. Okay, so at maximum efficiency the total losses will be 2 times Wi, not 2 times WCU or full load copper losses. Very, very important. Now let us have a look at this question. Let us have a look at this question. When a short circuit test is conducted on a single phase transformer, 30% of rated voltage is required to allow full load current. Okay, just 30% of voltage is enough. We are not applying rated voltage. The short circuit power factor is found to be 0.2. The short circuit power factor is found to be 0.2. The percentage regulation at unity power factor is dash. So here options, if options are not visible, the regulation, the percentage regulation at unity power factor, he has given it as 30%, 29.5%, 15% and 6%. Ashok is asking, Ashok is saying, okay, try to take up this type of classes till the exam, huh? Okay. Sure, Ashok, I'll definitely take up. But the thing is, we need more response. So when we have more response, definitely we will take up many classes. So when we do not find response, so it is not going to be a encouraging factor or boosting factor for us, no. So that's the main reason. Anyhow, so he's asking regulation. If you have an idea about the regulation graph, then you can answer this question. Regulation, percentage regulation and the power factor. On the right side it will be a lagging power factor, on the left side it will be a leading power factor. Okay, of course at the middle I can take up this power factor as unity, and when you go from the middle to or origin to the right side, the power factor decreases, maybe 0.8 or 0.6 and so on to the 0. And similarly here also 0.8 leading, 0.6 leading and 0 leading. If you remember the graph, regulation graph of the transformer or synchronous generator, it looks like this. At unity power factor, some positive regulation will be there. Now at any lagging power factor, the regulation will be always positive, and moreover, if the lagging nature increases, the regulation increases. Regulation means simply drop, and you can expect maximum regulation near to 0. And similarly, the regulation can be 0 at the leading power factor, especially greater than 0.9 leading, and it will become negative like this. So this is how the regulation graph looks like. Now if you look at the options, I can easily say the regulation of transformer will never be 30%. It's highly impossible. Synchronous generator regulation can be 30%, 29%. So transformer regulation is highly impossible to have 30% or 29.5%. That's the worst case. Even 15% also not possible. Even 15% also not possible. So let us take up that 15% at least. So you can eliminate two options. Okay. So by looking at this graph, at unity power factor, this regulation is asking. If you remember the formula, percentage regulation is equals to percentage R into cos phi plus or minus percentage reactance into sin phi. Okay. He is asking at unity power factor. If the power factor value is unity, sin component will be 0. So this component will be 0. Now the percentage regulation is equals to percentage resistance. Okay. Now from the given data, if you are able to calculate the percentage resistance, then you can calculate that is the value of percentage regulation. That is the value of percentage regulation. Okay. All right. So how do you find out this one? So if you remember the formula, the short circuit voltage can be taken as the short circuit current or rated current into Z01, impedance of the winding, R01 plus X01, J is X0. Alright. So if you divide this with the rated voltage, I can rewrite this equation as short circuit voltage with respect to the rated voltage. You can call it as per unit short circuit voltage is equals to Z01 divided by rated voltage, and this is a rated current. You can bring this rated current to the denominator, so it will be E1 by I1 or E1 by rated current. So E1 by rated voltage by rated current is nothing but V by I is nothing but impedance. So it forms like a base impedance. So Z01, I can write Z01 by E1 by ISC. So this is like a Z base. So actual value by base value, that can be written as again per unit impedance. Okay, you can convert into percentage. So into 100, that will be the percentage values. So the short circuit voltage in per unit, we can write it as 0.3. Now the percentage impedance will be directly equals to 0.3 simply. Okay, got it. What about he's asking about regulation. So regulation is equals to R. So how do you calculate the percentage regulation? You can calculate from another formula that is called cos phi. The power factor can be taken as percentage R by percentage Z. I know the percentage Z from this, so substitute here. So you'll get percentage R. Cos phi value is 0.2 into percentage Z is 0.3. So you will get it as 0.06. You'll get it as 6%. Okay. Is it clear for everyone? Very good, Ashok. Now let us take up one more question. The inrush current of a transformer is maximum when it is switched at an instant the voltage wave is passing through. Okay, so the transformer, we are going to switch on the transformer. When the voltage wave is passing through. When it is passing through 0, are you going to close the switch at 0 crossing, or are you going to close the switch at peak crossing? At which instant the inrush current of the transformer is going to be maximum? That is a question. Okay, so option A is 0 crossing. Okay, option A is 0 crossing, and option B is positive maximum crossing, and option C is negative maximum crossing, and option D is any value. Option D is any value. Please try to understand the question, what he is asking. He is expecting inrush current of a transformer is maximum inrush current. When will you get transients? When you close the switch at 0 crossing, or when you close the switch at peak crossing? If the voltage wave is passing through 0, which means if you are closing the switch, the applied voltage on the transformer is increasing. So you are applying a sudden change to the transformer. So definitely the windings will oppose a sudden change in currents, and it leads to the transients. Okay, I'll tell you, there is again doubling effect and all those things. Consequences will be there. Okay, I don't want to get into that, but the transients can take place at 0 crossing switching, but not at peak crossing switching. So you will get transient free response, or inrush currents will be minimum when you close the switch at peak crossing. Okay, so if the voltage wave passes through 0 crossing, you will get maximum inrush current. That's why we will call it as doubling effect and all those things. No, is it clear for everyone? Not B. B is not the answer. Sweta and Ashok, B is not the correct answer. If you have any doubts, you can ask me. If anybody has doubts, please ask me. Okay, so let us move on to the next question. I have a question as two transformers operating in parallel have different quality of their leakage impedances. So it's like the transformer windings will be having R01, X01, another transformer will be having R02 and X02, like that, or X01, X02, like that. For a load power factor of 0.8, now what could be this? What could be the answer? So the first option is both would operate at power factors less than 0.8. Both would operate at less than 0.8. Option B is both would operate at power factors more than 0.8. And option C, both would operate at same power factor. Both transformers, if it is not visible, I am writing both transformers power factor is same as load, that is 0.8. And the last option is transformer, one transformer, I am not saying transformer 1, it's like one transformer will operate greater than 0.8 and another transformer 2 will operate at less than 0.8. Another transformer will operate at less than 0.8. What could be the correct answer? Very good, Prasad, superb. See, he is saying that the leakage impedances are different. Okay, the leakage impedances are different. So simply it's like current division. Here I have a resistor, maybe 10 ohms and maybe 10 ohms. If the resistors are equal, then I can say the current can be equally divided. Okay, if 10 amperes of current is flowing, then 5 amperes will flow here and 5 amperes will flow here. Okay, same way leakage impedances also you can take up. If unequal impedances are there, what is going to happen? Definitely here let me write R and J maybe as 1 J1 and another one is going to be 1 J2. Let me take up like this. So obviously the impedance of first transformer is lesser and the impedance of second transformer is higher. Obviously the lesser impedance transformer can deliver more load or can share more current, can deliver more current. Yes or no? So I1 will be greater than I2. Load sharing will be done by the least impedance transformer. What is asking? He is asking about power factor. So if he is asking about power factor, let us look at the power factor. Let us look at the power factor. So I can say here, if I take up the voltage as reference, the current delivered by the first transformer 1 plus J1, impedance is going to be 1 plus J1 and current is I1. So I1 I am drawing at this point. And the angle between voltage and I1 is going to be some phi1. You will get it as 45 degrees because it is 1 plus J1 impedance. Okay. And I2 1 plus J2. So tan inverse of J2, how much you are going to get? Tan inverse of J2 or tan inverse of 2, you will be getting it as 63.43. So this is my I2 and the power factor angle is going to be 63.43. Yes or no? Now the combination of I1 and I2, that is transformer 1 and transformer 2, both are delivering a load. And this load power factor is 0.8 power factor. Okay, try to understand. So these two transformers are driving a common load of 0.8 power factor. So if I take a 0.8 means it's probably cos inverse of 0.8 will be 36.86, right? Cos inverse of 0.8 will be 36.86. I did not draw the exact phasor diagram because I have taken impedances 1 plus j1, 1 plus j2, a random value I have taken. So you see this power factor angle is something, this is a load power factor angle. So the load power factor angle is larger than first transformer and lesser than the second transformer. Phi L is greater than phi 1 but less than phi L is less than phi 2. So therefore I can say one transformer can operate at greater than load power factor, another transformer can operate at less than load power factor. So they cannot operate at same power factor. Operating load and the transformers operating at same power factors is not at all possible, and operating at less power factors, operating at high power factors also not possible. So option D is the only possibility. Okay, right. So there is a small announcement about the from BYJU'S exam platform, that is, if you feel BYJU'S exam prep gate course fees is very high very huge, if you feel that, then you can attempt the scholarship test so that you can get some discounts and concessions. And the scholarship can by writing the scholarship test, if you top the scholarship test, then you can get up to 90% of discount and concession will be there, So the scholarship test is on 18 June, maybe after 2 days. Yeah, and the scholarship test timing is 12 o'clock. If you have enrolled, that's fine. If your friends or colleagues are planning to enroll with the BYJU'S exam prep, tell them it is not costly. You can have so many ways to get the discounts. Okay. All right. So let's move on to the next question. Look at this question. The injected EMF in the rotor of induction motor must have. Option A, same frequency as the slip frequency. Option B, the same phase as the rotor EMF. Option C, higher value for satisfactory speed control. And option D is about the same phase as a rotor EMF. If it is not visible, I am writing same phase as rotor EMF and high value for satisfactory speed control. It's like B and combination of B and C. Option D is a combination of B and C. Okay, come on guys, respond. So if you have an idea about the rotor induced EMF frequency, FR is equals to slip times the F, supply frequency. Okay, rotor frequency is very, very small. Generally, hardly it won't cross more than 4 Hz also. Under no load condition, 1 Hz to 4 Hz will be there, because the rotor conductors are going to rotate near to the synchronous speed, and hence the slip is going to be very small. If the slip is very small, so if I take up the slip as around 1%, 1% of 50, you will get it as, you see 50 by 2, so you will get it as 0.5 Hertz. So it's very small. The rotor frequency is very small. Okay. Now injected EMF in the rotor of induction motor. This is there is a technique to control the speed of the induction motor. Okay. So if you want to inject an EMF externally through the rotor, into the rotor circuit through the slip rings, the injected EMF should have the same frequency. Otherwise, if you have different frequencies, there might be chance of getting harmonics, because induced EMF in the rotor will be 0.5 hertz, and if you are injecting 1 hertz or 50 hertz frequency EMF, then that's not going to good, right? So it looks like this. If the induced EMF in the rotor is like this, okay, this is the frequency, and if the injected frequency is this one, and if this is the rotor EMF free, if this is the induced EMF in the rotor, definitely that is going to create a harmonics. So the first most thing you need to satisfy is, to avoid the harmonics, the frequency must be same frequency as the rotor frequency. What is that rotor frequency? Slip frequency. Okay. Why not same phase? You can inject the EMF. If this is the rotor EMF, let me write it as E2. You can inject the EMF in phase. Okay, I'm sorry. You can inject the EMF in phase, or you can inject the EMF out of phase. But the condition to be satisfied is frequency. The time period of the time duration of the rotor EMF and injected EMF should be same. So option A is a correct answer. Very good, Sweta and Ashok. Others also please do respond. Okay. The next question. The mutual flux to the leakage flux ratio is larger for a transformer as compared to an induction motor, because a transformer has no moving parts, because the motor has air gap, and C, higher permeability material is used for the core of a transformer as compared to the stator and rotor cores of induction motor. And the option D is about, in induction motors the rotor windings move relatively to the stator windings. He is saying mutual flux to leakage flux ratio is larger in transformer compared to an induction motor. Why? If you look at induction motor and if you look at transformer, this is how it looks like, right? So let me show you the transformer core and windings. Okay. So if I give the supply, and that supply can create a flux, and this flux is going to link with the second winding. Coil 1, N1 coil flux lines are linking with the N2 coil flux lines, and hence whatever the flux lines linking with the coil 2, you can call them as mutual flux. We will write it as phi m. So what he is saying, the mutual flux to leakage flux ratio is larger in transformer. So there is a less chance of having leakage flux. There is a less chance of having leakage flux through this air gap, or establishment of leakage flux or establishment of flux around the coil is very less. Okay. And when it comes to induction motor, I have a stator and we will be having a rotor, and on the rotor I have conductors. Now between the stator and rotor we will be having air gap. The air gap is going to be hardly, it is not going to be 10 mm or 30 mm like that. Hardly it will be 2 mm, it will be less than 3 to 4 mm, that's not more than that. It can be 0.5 mm, 1 mm, 2 mm also, very 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 small. Okay. But still the mutual flux linkages from stator to rotor, mutual flux to leakage flux ratio is lesser in induction motor. Why? What is the main reason? Are you saying B is the answer? Motor air gap, because motor has air gap? That is also possible. Motor has a air gap. Because of air gap, reluctance is more. If reluctance is more, establishment of mutual flux is going to be lesser. And another option also I can say, transformer has no moving part. If transformer also has a moving part, we can expect again air gap, no. So transformer doesn't have a moving part, so therefore it's a continuous medium. It's a continuous medium, but most proper answer is motor has air gap. Okay, motor has air gap. Because of air gap, reluctance is going to be more. Right. Next question, coming to the next question. A 3-phase 4-pole 50 Hz induction motor runs at a speed of 1440 rpm. Runs at a speed of 1440 rpm. Okay. Now, first option is saying its slip is 0.04. Its rotor field rotates at 60 rpm with respect to the rotor. Its rotor field rotates at 60 rpm with respect to stator field. Its rotor runs at 60 rpm with respect to stator field. Its rotor field rotates at a speed of 1500 rpm with respect to stator. If fourth option and fifth option are not visible, I'll write aside. Fourth option is its rotor runs at a speed of 60 rpm with respect to stator field. Rotor runs at 60 rpm with respect to stator field, not stator field. And fifth option is its rotor field rotates at 1500 rpm with respect to stator. Now he is asking, from these correct statements are going to be, so option A 1, 2, 4, 5, option B 1, 2, 3, 4, 5, and option C 1, 2, 5. 1, 2, 5. Ashok is saying 1, 4, 5. Prasad is saying 1, 2, 5. Okay, let's look into this one. First thing, what is the synchronous speed? Can you tell me what is the synchronous speed? Ns is equals to 120 into 50, 120 F by P. Number of poles are 4, so you will get answer as synchronous speed as 1500 rpm. Okay. Now check for the slip. The slip will be, per unit slip will be Ns minus Nr, that is 1500 minus 1440 divided by 1500. Ns minus Nr divided by Ns. That's a per unit slip. So we will be getting 60 divided by 1500. Possibly 6 by 150. I think 6 by 150 could be 0.04. 6 by 150. Yeah, 0.04. It is coming at us 4%. So option 1 or the statement 1 is correct. Statement 1 is correct. Now the statement 2, its rotor field rotates at 60 rpm with respect to rotor. Whenever these kind of statements are given, please assign the speeds of those respective entities. Rotor will rotate at a speed of Nr. Rotor will rotate at a speed of Nr. Rotor field will not rotate at Nr. Rotor field is also going to rotate at synchronous speed. Now what is saying? The rotor field rotates at 60 rpm with respect to rotor. So let us compare. How much Ns minus Nr? Ns is 1500, Nr is 1440. So you will get 60 rpm. So option statement 2 is right. Rotor field, stator field, both will rotate at synchronous speed, but they will be delayed by some angle. Okay. So if rotor field is rotating at 1500 rpm and rotor surface or rotor is rotating at 1440 rpm, Now the difference speed is what? 60 rpm. Okay, so the rotor field rotates at 60 rpm with respect to rotor. The difference speed is how much? 60 rpm. Now the third statement is what? Its rotor field rotates at 60 rpm with respect to stator field. Rotor field speed is ns. Stator field speed is also ns. Now the difference is how much? Ns minus ns, you are going to get 0. But he has mentioned it as 60. So statement 3 is wrong. Statement 3 is wrong. Now what about statement 4? What about statement 4? The statement 4 is the rotor runs at a speed of 60 rpm with respect to the stator field. Rotor runs at 60 rpm. The rotor running at 60 rpm. That means what? What is the rotor speed? First of all, rotor speed is nr. With respect to stator field speed is how much? Ns. You take the difference, nr minus ns, that is 1440 minus 1500, you are going to get again 60 rpm. You are going to get 60 rpm. So the rotor runs at 60 rpm with respect to the stator field. No doubt, this is also correct answer. Don't expect negative 60, positive 60. Difference is 60. Okay. So according to fourth statement, rotor is lag by 60 rpm, I can say. Rotor is going to lag by 60 rpm with respect to the stator field. Okay. What about fifth statement? The fifth statement is rotor field rotates at synchronous speed. So he is saying rotor field rotates at 1500 rpm with respect to stator. What is the stator speed? 0. So ns minus 0 is going to be ns. So you will get 1500. So the fifth statement is right. Rotor field is going to rotate at 1500 rpm with respect to the stator. Okay. So I can say statement 1, 2, 4, 5 are correct. Option A is the correct answer. Very good, Chandu. Superb. If anybody has doubt in this one, please ask me. Please post your doubts or comments. If you do not understand at any point, you can post your comments or doubts in the comment section. Okay. Ashok, are you there? Okay. Sweta, Ashok, Prasad, respond. Right. Let us look at next question. In case of 3-phase induction motor, shaft power is 2700 watts and mechanical losses are 180 watts. At a slip of 4%, the rotor ohmic losses are. Option A 115.2, option B 120. If it is not visible, let me write. Option B is 120 and option C is 108. Option C is 108 and option D is 105. Tell me. If you remember the power flow diagram, then it is very easy. We will give the supply to the stator. So let me write it as stator input. SI, stator input. After giving the stator input, or you can also call it as motor input. After giving the input, some loss is going to be taken place in the stator in terms of iron losses and copper losses. On the stator you will be having armature winding, so copper losses will be there also. So I am writing it as stator losses, SL, stator losses. And the remaining power will be transferred from stator to rotor via air gap. So we call that power as air gap power, or I can also call it as rotor input power. Air gap power, or I can also call it as rotor input power, RI, rotor input power. Now once the rotor is going to receive the power, then definitely rotor gets magnetized. Some amount of iron losses and copper losses will take place on the rotor too. But generally the rotor frequency is very small, and hence the rotor iron loss are very small, because rotor frequency is hardly 1 Hz or 2 Hz. So the iron losses in the rotor, that is hysteresis loss and eddy current losses at small frequency, is almost neglected, and that's the reason why we write the losses as only rotor copper losses. We never write rotor iron losses, but here iron losses we will take up, and here we will take up copper losses also at the stator. We don't take up iron losses in the rotor because of small frequency. And then whatever the remaining amount of power is there, that power we call it as gross mechanical power, and this gross mechanical power will be transferred to the shaft. Now the shaft is about to rotate, but to rotate, or to get the rotation, it has to overcome the friction and windage losses. So we call them as mechanical losses, and after the mechanical losses, the power is called as shaft power, or output power, or motor output power. What is asking? Rotor ohmic losses. So this one is asking. So if you want this one, there is a relation between the rotor input power, gross mechanical power, and copper losses. Rotor input power, rotor copper losses, and rotor gross mechanical power. It is like 1:2, S:2, 1 minus S, if you remember. Now I want this rotor copper losses. So rotor copper losses will be S into gross mechanical power divided by 1 minus S. I know the slip 4%. So I can write 0.04 divided by 1 minus 0.04. 1 minus 0.04 is 0.96. 0.04 divided by 0.96. So I can write it as 4 by 96. Into 100 you can write. Okay. Into the PGM. What is the gross mechanical power? The gross mechanical power will be shaft power plus mechanical power. Shaft power is 2700 watts. Mechanical power is 180 watts. So 2700 plus 180, you are going to get it as 2880 watts. So if you solve this, you will get the answer. Anybody got the answer? 115.5. Is it 108 or 105? Chandu is saying 105, Ashok is saying 115, Prasad is saying 120. Please calculate this. 96 and 4, any ways are there? 4 2s, 4 4s, it's 12. Sorry, 4 2s are 8 and 1 remaining, 4 4s, 24s. 24. 2800, sorry, 2880 divided by 24. Maybe 200s or near, not even 200s also. 2880 divided by 24. 120. Exactly going. Sai Krishna, congratulations Sai Krishna. Thank you. 120 watts is the answer. Okay. Now if you look at this question, starting torque of a 3-phase induction motor varies as. Starting torque of a 3-phase induction motor varies as. It's like proportional to frequency, inversely proportional to frequency, and inversely proportional to square of the frequency, inversely proportional to cube of the frequency. If it is not visible, C option is going to be A option F, B option 1 by F, C option F square, 1 by F square, and D option 1 by F cube. First thing, especially if you want to find out maximum torque quantities or some relations, full load torque or otherwise starting torque, the most important formula you need to remember is the electromagnetic torque equation. First of all, the electromagnetic torque produced in the induction machine, 180 by 2 pi ns into S into E2 square divided by R2 square, approximate torque equation only, R2 square plus S times X2 whole square. What is asking? He is asking starting torque. At starting slip is 1. At starting slip is 1. So this can be replaced with 1. And moreover, if you see, generally the rotor resistance is a smaller value and compared to the rotor reactance. So therefore, if I neglect the resistance, the formula can be rewritten as 180 by 2 pi ns into E2 square divided by X2 square. Okay, so this is my electromagnetic torque at starting, or let me write it as starting torque, because I substituted slip. I have taken the slip value as 1. Now if you see, synchronous speed is a function of frequency, 120f by p. So synchronous speed is proportional to frequency, and of course the reactance is also proportional to frequency, because reactance or inductive reactance is generally 2 pi fl. So here x2 square term is there, so 2 f terms you can expect, and ns term is there, 1 f term is there. So overall on the denominator, in the denominator we have 3 frequency terms. So I can write the starting torque is inversely proportional to frequency cube, directly proportional to voltage square, directly proportional to square of the voltage, and inversely proportional to frequency cube. Very good, Akbar. Chandu, it is not B. Akbar, you have given the answer many times. Sweta, it is not B. D is the correct answer. Prasad, very good. Now let us move on to the next question. I have one more question, that is, when a 3-phase induction motor is loaded, so the induction motor is running, right? Maybe it will run at something near to synchronous speed under no load, you just imagine. Okay, so this is your torque speed characteristics of induction motor, and the induction motor will run at some speed near to the synchronous speed. Let us take up this as no load speed. This is the no load speed, and I can say this is the no load torque. Okay, what is saying, when the 3-phase induction motor is loaded, so if it is going to be loaded, so increase the load from no load to half load or 75% load or full load, like that. What is going to happen? The rotor, earlier if it is running at 1440 rpm or 1450 rpm, now definitely if the load increases, definitely the speed will decrease. It may come down to 1410 rpm or 1420 rpm, like that. So the rotor speed is going to be decreases. Now what are the options he is asking? What are the options he has given? Induced EMF in the rotor decreases and its frequency increases. Induced EMF in the rotor increases and its frequency falls. Option C is induced EMF in the rotor, that is E2 and F2, that is FR, both falls. And option D, induced EMF as well as frequency, E2 under running condition and F2 under running condition, both will increase. Tell me now, if the load increases, no doubt the speed will decrease. If the speed decreases, what will happen to slip? The load increases, no doubt the speed decreases, NR decreases. If NR decreases, what will happen to the slip? Slip will increase definitely. If the slip increases, if the relative speed increases, more flux cutting action will take place, and therefore more amount of EMF will increase, will induce. So if slip increases, the induced EMF under running condition also increases, because induced EMF E to R is equal to S times E2. Similarly, frequency also is equals to S times F. So if the slip increases, no doubt the induced EMF and the frequency both will increase. Option D is the correct answer. E2 is also proportional to F. Yes. Oh, I did not get you. E2 also proportional to F. Chandu, where you are asking? E2 is a slip dependent. The induced EMF is a slip dependent, not don't relate with the frequency. E2 is a slip dependent. Chandu, is that clear? V by F constant. Chandu. See, Chandu, these are the parameters, these are the quantities which are going to change in the rotor, okay, not on the stator side. The V by F control, keeping the V by F control as constant means that is, you can keep it on the stator side, not on the induced EMF in the rotor and frequency of the rotor. Chandu. Okay, you are saying about previous question? Okay. Okay. That's a good point. When it comes to if V by F ratio is constant, then gone case. Starting torque is V by F whole square. You can make it as constant and you can write it as 1 by F. But generally they did not mention no V by F as constant. So if they mention, they can, then you can, then this is the answer. If V by F ratio is constant, then option B is the correct answer. In general, it is inversely proportional to frequency Q. Very good, Chandu. Next question. Okay. Look at this one. With a constant line voltage V, the powers at starting drawn by a three-phase induction motor, when first run in star connection and then run in delta connection, are P1 and P2. So if I have a star connection, the power consumption is P1. If I have a delta connection, the power consumption is P2. Now the relation is asking. What is saying? The source is same. The source is same, three-phase source, and its voltage source, it is same. So what we are doing is, we are connecting the motor in star connection. Okay, it is same like in networks also, the same way you can take up. I have a star connection stator winding. I am not showing the rotor, so let me join this. Dot is a connection and no dot is not a connection, no connection. If there is no dot, there is no connection. So the power consumption by the star connection is P1. Now the power consumption by the delta connection is going to be P2. That is what he is saying. Okay. Now in which case the motor will consume, more power? If you remember, the line current and phase current in the star connection both are same, but the line current and phase current are not same in the delta connection. The line current is √3 times the phase current. Yes or no? If you remember, the line current and phase current in the star connection is same, but the line current and phase current in the delta connection is not same. So the line current is √3 times the phase current. The applied voltage across the delta phase and the applied voltage across the star phase, or the line voltage, I can say, the applied voltage across the line in the star connection, the applied voltage across the line in the delta connection, voltages are same. If it is 440 volts, 440 volts is applied across these two lines. 440 volts applied across these two lines, but the current drawn by the star connection and delta connection are not same. Delta is drawing more current than star, so definitely the power drawn by the delta connection is definitely greater than power drawn by the star connection. So if you compare the currents, then you will get the answer. Okay, so P2 is definitely greater than P1. P2 is definitely greater than P1. So P2 is not equal to P1. How much is that? How much is that? Option C, that is 3 times the P1. If you compare star connection current and delta connection current, You will get star connection will draw 1/3 of delta connection. Yes or no? If you remember, then you can answer it. Yeah, Akbar, actually, I have to hide myself. I am not able to hide myself. I forgot the key. There is a key actually to hide myself. Let me check. Let me check. Video capture. Yes, I think this is now hidden. Yes. If anybody has doubt about this power consumptions, please do let me know. Okay. I just said from the current values only. Delta connection is drawing much more current than the star connection. So definitely the power drawn by the delta connection will be greater than power drawn by the star connection. So if you compare star connection current and delta connection current, you will get 3 times. The current drawn by the star, connection is actually 1/3 of current drawn by the delta connection. So as a current is 3 times, delta connection current is 3 times the star connection. So I can say the power also, the power drawn by the delta connection is 3 times the power drawn by the star connection. Okay. So let us move on to the next question. So this question is on single phase induction machines. The type of single phase induction motor having the highest power factor at full load is. Okay. We want highest power factor. If you want highest power factor, the only thing is more capacitive nature or less inductive nature. Highest power factor is nothing but more capacitive nature. It's not even more capacitive nature also. Better I'll write it as more resistive nature. Highest power factor means unity power factor is the highest value. So when will you get highest value? If it is very close to resistive nature, then obviously you can get it. How do you get more resistive nature in the induction machines? So when you keep a capacitor in series with the windings, generally this is going to be the main winding, or we can also call it as a running winding, and we will be having auxiliary winding or starting winding, and in series with this we will be having a capacitor. Okay, right. So this, if capacitor is there, the inductive reactance of the winding will be minimized, and hence the nature of the winding will be more resistive nature, and hence the power factor will be close to a higher value or a unity value. Okay, or higher value. So what could be the correct answer? Whether it is shaded pole type or split phase type or capacitor start or capacitor run. In which induction machine you are going to get more power factor? Very good. No, Akbar, it is not split phase. Split phase is nothing but simply you can split the phases by having an extra winding. That's it. Resistance split is also there. Okay. So generally you don't get much power factor with that resistance split. Split phase is not possible. Shaded pole is also not possible. So the induction motor must consist of a capacitor. Okay. So whether it should be at starting or at running. Generally at full load, if you are expecting high power factor, so let us keep the capacitor under running condition also. So if you keep the capacitor under running condition, then it is possible to get more power factor. If capacitor is there, more power factor is possible. If capacitor is not there, less power factor. Okay. So capacitor run is the answer, not capacitor start. Okay. So that's all. I have got around 17 to 18, I think 17 questions I have discussed. And this is all about workshop. uh, if you are planning to crack, if you are planning to appear for gate examination or engineering service examination, BYJU'S exam prep is going to give you is going to conduct some workshop how to crack the gate in 8 months, and it will be taken by Rakesh sir, and the session will be on 20th June. The session will be on 20th June and the timings will be 7:30 p.m. Okay, so please try to attend this session and try to, I think this will definitely help you to crack the gate examination. He'll definitely discuss about the tips and tricks to crack the gate examination. Okay, so that's all from my side. I have covered I tried to cover some questions, okay, of transformers and induction machines. So in the next session I'll try to cover DC machines and synchronous machines if it is possible. I think this session went on around 1.5 hours. Okay, generally I'll take the session very slowly. Let me speed up the session. In the next session I'll try to finish it by 45 minutes. Anyhow, if you have any doubts at any point, you can take up that screenshot and you can send it to my mail ID naveen.gollapalli@byju's.com. Thank you so much. Have a nice day. If you have any doubts, you can ask me. Yeah, Prasad, split phase will give you revolving field. That is fine. See, splitting the phase can be done by connecting an extra winding. Okay, by connecting an extra winding. So it's like this. I said no, the main winding will be having some resistance and reactance. So you take an extra winding, that winding also will be having some resistance and reactance. So the current flowing through this winding and the current flowing through this winding will be differ by some angle, because this resistance will be 1 plus J1, let us assume, and this resistance will be around 0.2 plus J let me take up around 0.3. So the phase angle I1 at an angle theta 1 and I2 at an angle theta 2 are definitely different because their impedances are different, and that's what the split is with respect to voltage I1 and I2. This is what the split is. So the split between the windings, that is I1 and I2, this alpha creates the torque, because I1 will create one flux phi1 and I2 will create flux phi2. So the interaction of phi1 and phi2 will create the torque, because of it depends upon alpha, and the alpha generally it won't exceed more than 40 degrees, 30 to 40 degrees, because of just extra winding. If you want to increase the alpha, then add a capacitor, then alpha increases. Along with that, the additional advantage is power factor, because addition of capacitor will nullify the reactance nature, and therefore the power factor can be enhanced. It will be little more. Okay, he's asking about power factor, so I just said about power factor. Okay, not about torque. Okay, Prasad, if you have any doubts, please ask me. Prasad. Chandu, I teach generally networks, I teach measurements, I teach machines, I teach power systems. Power systems very rare. Generally I'll take up free sessions, not paid session. Okay, all right, chalo then. Thank you so much. Have a nice day. Bye bye. See you everyone. Why is it not stopping?